Start recording. Okay, good. So, as you might remember, the last time we were improving on our and finishing our shellcode, and the state as we left it off was functional but very basic. So, I think since we only have this one lecture and starting something new probably will take longer than one lecture, we should just continue on improving what we already started. There are a few things that we can definitely do to make it significantly better, and also, as you may remember from the lecture before that, our way of hooking functions was very, very manual, which, while it of course works and is a viable option if you have just a handful of functions to hook, is not really usually the preferred solution. So the way it is done in production is that you use some library that is complicated enough so that it is able to hook any API function you might throw at it, and it would automatically generate the necessary trampoline calculating the offsets, etc., etc. So such a library usually is not quite trivial, so it needs some level of being able to decompile or at least disassemble the prolog of the function which it is hooking, and then have enough internal logic to be able to devise which offsets needs to be changed, which displacement needs to be added, etc., etc. So it is quite a complicated thing, but luckily there are such libraries available. So a good start would be to take a look on two of those libraries that one can use, as this will make it much simpler for you in future to hook functions if you would ever want to do this. And one of them is a rather old library. Here on GitHub, I will put the links into the chat as well. This is a library some guy a long time ago made, even before GitHub, and then it was moved to GitHub. And it is reasonably simple. It is not really capable of hooking anything, but it should be capable of hooking any Windows API function, which for the most use cases it is good enough. And there is also a second library provided by Microsoft themselves, which is generic, so it can really hook any API, any function you might throw at it from any library. And the most important difference is that this one also supports ARM64. So if you want to hook some thing on a very modern system, then you can use this library as well. The other library is much more handcrafted and only supports 32-bit and 64-bit Intel architecture. And the main difference between those libraries, by the way, how they are made, is that the Minhook library is kind of handmade. So apparently the guy just looked on a lot of API functions or used some automated means, and for the types of function prologs which you can encounter in the Windows API, just a handful handmade template solutions have been added to the library, and it expects those. If the prolog of the function would be completely different, then it would not be able to handle it, while the Microsoft library uses the full decompiling and updating and recompiling approach, so it is much more sophisticated. If you compare those libraries, you will also see that it uses much more. There are much more files and much more code that is used for all of that. We can, in principle, use any of those in our projects if we want to. They come with examples, so we don't necessarily need to go through those examples. It's just good to know those. And I would say that first we will continue on our shellcode, and then if we have time left, we will maybe take a look on using one of those libraries instead of our manual approach. What also is quite a funny thing is that sometimes you might have scenarios where you want to start an application which will then start another application, and you want the hook that you want to install to propagate or something like that. So in this case you would hook the create internal process W function, and this way you can kind of inject your code into any program which is spawned by the programs where your code was already injected into. So we can take a look on adding this functionality to our system as well. But first let's take a look on improving our existing code. So first thing that we would want to improve is that we would want to add some optional parameters. So since we can now call an arbitrary function, the function can also take one or more parameters. Obviously, for simplicity, we will just go with using one parameter. There is no real benefit in our use case of being able to specify like 2 or 3 parameters, assuming that the DLL is made by us and we can just put all the relevant values into one structure, which is then passed by the first argument. And then the next improvement will be that we will try to get rid of this additional memory allocation, and then just really put everything into one large chunk of data. That will also help us make this more elegant. So first things first, convert parameter and size t small t param size. Then we should of course use this somehow. So I mean, for simplicity we can just use a string. Let's go like this. My param equals doesn't need to be anything particularly complicated, just for testing. So comma this, comma size of gives us the size in bytes, including the terminating null, so it's perfect for what we want to do here. Okay, so we have our parameters, we have our size. Then we have those things that we want to get rid of to some extent as well. So what we will do is here where we write the addresses, this one and that one, we'll create 2 new variables to hold some helper data. Where's a good place? Okay, then let's say here let's go with the right data type from the get-go. So this we have defined as q-int64, so q-int64 asterisk pin. First was DL path address, so DL the path, oops, DL path okay. Initialize, so this of course for starters, and the other is func name pointer. Func name pointer. Now instead of assigning the value here, we'll just save the address, DL path, and the other one was func pointer, so that we can edit it later on. Okay. So we have the addresses, and now what we will do is here we need to calculate a new length, so we can move some of the stuff downwards. So this can go, this we will grab for now, and the next step will be of course adding the for size we need. So let's leave it on the top for the other because we need the size and stuff for other applications. But this one we don't need, this one we don't need, we only need this one, we only need the sizes. data size, we also don't need those two sizes here at the beginning. Yeah. But we can copy the this line because most of it we will reuse. So we are here done with our code. Let's put them here first now, but we are not yet fully done. So we could, in principle, just for elegant purposes, pad the code somewhat, so that we just add a lot of knobs at the end. And we can later improve this so that we can like go to some nice offset, but for now let's just leave it like this so that we can easily recognize the position. So now we will need to have the whole length of the code, so the whole length is this, so let's call this shellcode length. Or actually what we also could do is we could just go to, we could just take the maximum length which we have pre-allocated. This is also a acceptable solution instead. Actually we could just go with size. We can comment this out and go with this was yes, normal array, so size of will give us the right value. We can afford to waste some bytes, so we have our shellcode length, then we have of course then our path size plus terminating char, then function name plus terminating char, and then we will add our parameter of which the size we already know, and the whole thing will be just then our new length for the memory block that we want to allocate. So we allocate the large memory block, page execute read write, so we can do whatever I want with it. That is as it should be. Now before we write the process memory, we will now calculate a few addresses that we will need. So actually let's stick to the old naming. I think I did not save the file yet, so let's what was it? No, that was with the copy those two functions because I'm too lazy to retype them. Right. So the DL path will be basically the address, so right, address plus size of shellcode. That's the address of the DL path. The next address will be this thing plus size of DL path, which is correct, and the next one, which we don't have yet, will be param, which will be a func name address. DL path set, but func name size. Are we happy with that? Wait, the sizes we have specified, these are the sizes as they are needed for the normal for the Unicode string, so we should add here our terminating zeros as well, plus size of char t, and to the other one we add size of char. Okay, so now we have the right addresses. For the parameters, we cannot do anything with it yet, since we have not yet added this to our code. But for the other two, we can already grab those pointers and assign them with the right values. Asterisk. This one is 64 func name address, and the other one will be wait, that was wrong, that's the right one. API path function, of course, so they don't need to be in brackets. And the next, of course, to do parameters. Okay. Good. And now we can write the data. So I think I could have kept the other write lines, those two. Right, so we write the shellcode at starting address 0, which is correct, and then we add those addresses, path name +1 size. Yeah, I mean, we could in principle like put everything into one buffer and then write it in one go, but at this point it does not make a difference. It will be marginally slower, but this is fine. The main idea is to just not have too many memory regions laying around in your in the process afterwards. What we could even do is, after we are in our main DLL, we could add some additional hook to the DLL such that we can later unload this whole shellcode from memory. We cannot do it while we are executing it, so we cannot do it from the function inside the DLL which we are calling, but we could, for example, do it from this DL main on thread attached. So we could assume that there will be certainly very soon some additional threads created, and at this point we would already be out of this code, and then we could unload it, or we could use a DLL to then hook the entry point of the process, but we are already in the entry point from now. Well, it certainly has some complexity to find out a good place to unload this, but we could, for example, set a timer that will just call a function in our DLL after some time, and then we would do the unloading or other things like that. So there are many ways how we could get rid of this memory if we really don't want it to still be there. Let's see. So we have done this. We have done this. So in principle, it should still work. We shouldn't have broken anything yet. So here we have commented out the interrupt. So we should be able to just run it, and it should just do what it was doing before. Yep, as you see, the hook is still working because it tells us just that the app is running fine, if instead of showing what was the main function, hook test, instead of providing a question and then doing other things. So this here works all fine. So the next step will be to add the parameter. You go to our DLL main, and then our install hook function will get one argument, void asterisk param, and since we want to be as efficient as we want, as we can, then we are not like having a second parameter containing, for example, the size of the param data, because this kind of is redundant. We can have, first of all, if we just pass a string, as we actually do. So let's dash 10 as param. Then we can just, based on the terminating null device where the string ends, and we can of course then, or we could of course pass a Unicode string packed together in one, or rather a Unicode string-like thing, because we don't have the address, but something that resembles a Unicode string that is packed together and contains the length parameter. Or we could have a complex structure where one of the fields, which we definitely know, will be the length for the arbitrary additional data, etc., etc. So it's not necessary here to have this size. The size was only needed so that we know how much data to copy over. So let's look at our function here. We have registers, right? So we have here our function call, and yeah, so The function called was a function. We'll check for errors and jump to end. This comment is not we copied it from somewhere. It should be here, I think. It's the comment slipped down. Not procedure. No, wait. Call written. That's in the right place. Just don't do anything else. This should have been here. That because it must be the opposite order. So we create we put the call not quite where it should be. That's why I was a bit confused. Here for a second. Yeah. Interestingly, this time, even without adding this space, our function did not crash. But as we have seen earlier, with wrong stack alignment, it actually crashes. We should not use done twice. It's called this finish and the other one called done, because this code here is just unrolling our stack modifications and restoring registers and then resuming execution. So and here we are finished with what we actually initially intended to do. So here we will add the one additional argument, and we do it with a load instruction. We have one here. Layer. We don't have a layer, so let's make one. Layer RCX, as we remember, is the first entry, first register. I mean, so here. This one is the closest to the other one, so let's see what's the difference. 448D. Okay, this one byte is different. 0D. Capital D, so it looks nicer. And here is DL base, but not function name offset, but we'll need to put a pointer here somewhere. If here a spare keyword, so let's use this one. Now function that makes sense. Param offset data plus plus, and this one gets assigned. That one doesn't get anything assigned. We don't know yet what it will be. Param instead of being assigned anything, we just grab the position, then we're here at plus 80. Function address, right, this will be resolved from the other function. That is fine. Param offset. So here, wait, where were we? As all of this should be much better commented. I think it's not ideal that it's so hard to read of a code. And it was a param offset. It was close to param offset. Param pointer is a param address, and we need to write this as well. So param address void, that's already void. Param and param size. Param. Yeah. Good. Okay. So when we run it now, it should end here in the breakpoint, and s param should be our what have I made it? Something test. Test 1, 2, 3. Let's be highly optimistic about what we did. Close but no cigar. What did we scrub? What did we scrub? I guess it's yeah, we passed the wrong thing. We put the address to where the thing would be. Alright, we don't need a layer. We should use just a normal we should have used just a normal move, because we don't want the address there, we want the value. So we don't want the address of it, we want the value, just that here with the other offset. That should be fine. Et voila. So again, the move operation moves data from somewhere to a register, or from a register to somewhere, while the load address will just give you an address of whatever you specified. And here we of course wanted the value, because the value already is the address of the string. Before, what we got was the pointer to the pointer, but we could have dereferenced param twice, and we would also have ended up with the right parameter. And of course, as mentioned, we could now use any arbitrarily more complicated sort of data structure. It doesn't need to be a string, it could be anything, as long as it is self-contained, in the sense that it does not point to anything other than to anything other. So this of course is a bit limiting, because then, for example, if you make a struct, then you will have for all the fields maximal lengths. But what you of course could do is that you would just, similarly as we did here, just have your struct, and after the struct have the arbitrary length fields, and then the struct would have pointers to those not pointers, offsets of these fields, so that you can reconstruct pointers wherever this memory then gets copied. This is generally the main limitation of structs which contain pointers, that they can no longer, as a memory block, be copied somewhere arbitrarily somewhere else, because they always rely on some additional memory which might not be yet allocated. Of course, another approach would be from the calling function to allocate some memory and then put your parameters there. So there are many ways how this can be made more elegant. And of course, then now the next step will be to add some error handling. But first, are there any questions? Okay, no questions. So the next, as mentioned, for the error message thing that we will need to consider is to do we want our code just to terminate silently, or rather not terminate, but just execute the original code without applying the hook, or do we want it to terminate the application, and if so, do we want to display some sort of error message or not? And for displaying messages, while it might seem easy to use just message box W, when we are injecting early enough, the user32 DLL may not be yet available, and we will probably not want to load from our shellcode yet another DLL just to display a error message. So we would need some function that is ideally provided in the NTDLL DLL to show an error message, and there in fact is such a function. It works a bit in a convoluted way, the anti-raise hard error function, because the way it works is that the process itself might be in the too early initialization state to display anything itself. So the message box actually is then displayed by one of the Windows session runtime components, and we just trigger that this happens. Let's just see. do we have the list of parameters? Here we have the function defined. So it takes an error status, it takes a number of parameters, a parameter mask, response options. Ideally, we could make it maybe such that we can, in fact, have like yes, no, cancel or something like that. And as you see here, it takes a, it returns us a response value. So that actually looks reasonably reasonable, let's say. So let's first make a small test project to, or actually we can use our existing test project just to test it, what parameters we need to feed it so that it does what we want, etc, etc. So here let's add a void test, just something that we can call at the beginning to do some testing. Right, so we grab our definition. We should put it somewhere. Right, we had a file for the definitions, but this doesn't help us since, I mean, it is of course nice to have. We can put it there as well, but first of all, this doesn't need to be commented out. But we will need a definition here so that we can actually use it and call it. This I do not like. Let's call it just p underscore. Yeah. And maybe for niceness, let's let's format let's format it like this so that we have so that we easily see, even if we have a bit of a smaller screen here on the VM, what parameters we need to specify. So first of all, we need to get it. So thing it's procedure address module get module handle w l enter dll.dll comma procedure is this, right? No, Mixer 0, just a breakpoint. Let's first see if we load it correctly. Yep, that loaded fine. So let's use it. Let's see how to use it. This should be status. Response is okay. We don't need a random error code. We can use some reasonable error code. Status. We need to include the right thing to make a status. That's annoying. This would be a nice error code. That's in the we should have not include that internal. I'm worried that when I include WinNTH that this will conflict with something. Let's see if it works. Right, and we already had a nice status. Status code somewhere in our. Okay, right. Apparently the other parameters we don't need. So number, we could probably display some additional Unicode strings which we don't need. No, that will be actually different. This thing, I think it will try to it will get a message from the system, from the list of system messages, and the messages display strings in selected positions. So we would need to know how the appropriate error message for this thing is formatted to know how many parameters we need to specify. But for now, let's leave it as is. No, that will definitely the parameter. Let's try to do it correctly. So, what does this take as a parameter? Ulong. Okay, so ulong. Ulong. That's wrong. PTR. The params. Parameters. Params. With one entry. The entry will be some DLL path. PTR. L. Doesn't need to be a real path. Right. Okay, so number of parameters 1. Unicode parameter mask. I don't know, let's go with 1 as well. Parameters will be a pointer on that. And then response options. That's the fun thing about using undocumented functions. I have no idea what to specify. But since they probably had a message box, so let's go with number 6. And I think there should be another parameter, but I don't know if this is defined, it's not defined. That will force it to always show a message box if we add towards 0, 1, 1. Wait, how many zeros is that? No, that is a little wrong. That must be 3 more zeros. 1, 2, 3. And this should be, if I'm not mistaken, this flag. So it doesn't like our params. Why? Pay ulong PTR. This is already as a reference because it's an array. Okay. Yeah. Let's keep the breakpoint here. And let's run it. Well, it did not show any message box. It was not happy with the arguments and it gave us an error of 50. Sorry, error 5. This is it's not listed here. Was that in test status? Remember the right header where all the status codes are defined. Was the NT just contains a few of them? That was good. And the status is right. And so it was 0C 1 2 3 4 5 6 5. Wait, 0C. Status access violation. Okay, that's not a good error message. So it's not happy with what we told. I mean, for now, for status, we could start with 0 0 0 and just see if we get any message box, and then we'll continue improving the code. Nope. Now we have a different error. 61. No, x 1 2 3 4 5 61. Status privilege not held. I would have assumed we don't need any privileges to display an error message, but they actually here in the example also, I think, set some privileges. Which one? Well, they just use a number without telling us which one it is. This is annoying. But for simplicity, let's try this with a different parameter. Oops. 1 yeah, so if we get, well, we get some error message, unexpected parameters, but at least we got a message box error. And I guess it's not happy that the other ones are missing, so we should go here back to our reference params. But now it was suppressed again. We get the we can try without that. It still is not happy. Why wouldn't it be happy? It gets number of parameters. Right, this might be wrong, so let's try 0. Parameters is a pointer to an array of parameters, which... Oh, wait. That, I guess that will take Unicode strings, obviously, since it's a... that will definitely take Unicode strings, that's why it's not happy. Okay. Unicode string, param1. Reference. RTL. Init string. There was a Unicode initialization function that was quite convenient. What was its name? RTL. RTL. Yeah, that sounds like I was typing it correctly. Maybe we are missing a header because the IntelliSense did not tell us of it. No, it's there. Now it's there. The nice thing is that this thing takes a normal string, a normal boring string, and then turns it into a Unicode string. Without even memory allocation, it just sets the fields and buffer points to this, and that's it. Okay, params. We have here our message box, and we should probably re-add the piece of code we removed before. And I will just save this for now. Let's see what we get now. Okay, something's not quite right. It's missing the RTL init Unicode string import. Link import. Let's add it to all of the projects. Much. I think it's located in the NTDL. Yeah. Okay, now we have a proper error message. And it's even in German, it's even localized automatically. Well, it's the same language as the operating system. But we only can press OK, and then we cannot do anything else. So the response we get, well, 6, whatever that means. But the question is if we can make this somehow offer us a choice. Let's just see what happens if we 2. With 2 we have a choice. Okay, so let's take OK. OK gives us still 6, so cancel will then probably give us... It gives us a different number, 3. That is already a progress, so let's see. Well, OK and abbrechen. Let's see what it tells us if we specify. And you see, I killed the program is dead, and the message box is still around because it's not generated by the program itself. Oh wait, I do not have a window finder here. I should add a window finder. no, not SATA. CRS, RSS. Yeah, this one. One of those two, I think it is Windows. This doesn't have any Windows, and this one has a So this second client-server runtime process, CSRSS of Windows. So when we trigger this function in any program, the kernel will send to the client-server runtime process responsible for the current session a message to display a message box with some predefined content. And we see even here when we inspect the windows, it has that which ones what it needs, and we can also see here somewhere this is already enabled. Session ID, of course it's not. Options, session ID. So on Windows, you can have different sessions. So session 0 is for the system. It's where the WinLog on desktop lives. So when you that's annoying. When I press any key combo to lock the screen, to lock my actual screen, not just the VM, but I can lock it. The message was now also shown on the session 0 desktop. But the main thing is here that the desktop you saw there where you can enter the password, that's the desktop 0. And the session 1 is for the first user that logs in. If we would now log in another user, I don't think I have another user on the system here, but then it would get session 2 and they are just incremented. And the way this is organized is that every session has their own Windows station and multiple own desktop objects. You can in fact switch between them, although this does not really work nicely since Windows 10, because the way the Explorer works is that it kind of uses already running helper process to display things, and it communicates with them. So if you open on your second desktop an Explorer and then some menus, when it tries to render them, it will still render them on the default desktop for your session. We can actually here in this tool even see, when we go to this option, how many desktops you right now have on the system. So we have here the WinLog on desktop and the default desktop, and that is it. And also here the sessions service, that's the WinLog on session and console. This is our current logged in user. But anyhow, the point is, if you create more more users at the same time, each of them will get an own CSRSS process, such that they are able then to display the message boxes, because you cannot, from a process which is connected to one Windows station, display something on a different Windows station. It doesn't work. But this much to our detour. Let's now try what if we get other message boxes, if we try other values. So wiederholen und abbrechen, that's also quite nice. Repeat and cancel. It's a pity that I don't find the documentation for all the options. Oh, yes, no sounds even better. We cannot provide a custom text. So we kind of don't know what yes and what no would do. Because what we would want is actually, we want to ask the user, do you want to continue without the hook being installed? And then yes, no would be the best option. But let's see what else we can see. Let's see 5. So 6 we knew 6 doesn't work. Yes, no, cancel, even better. And 6 doesn't work because it says we don't have the right privileges, and I think the reason for that is that the sample here, which we have here, I'm not sure. I won't speculate without being sure. We could of course see if we can find the documentation. But it's very likely that it will not be. Hard response option. That's what we need. Hello, perfect. Where did they find this? Okay, they found it where you can find anything in the System Informer repository. They have reverse engineered a huge lot of Windows thingies. Right, so 0, 1, 2, 3, 4, 5. Shutdown system, yeah, so that's why we would need special privileges. Okay, no, wait, that sounds like a cancel, try, continue. So which one do we like the most? Well, abort with ignore is also not so bad. I mean, yes, no sounds like the closest thing we reasonably might want to use. It just gives us two options, which is good enough. Or we could use OK cancel, like OK, kind of OK, like we're accepting whatever the error message, and cancel suggests that the application will quit. So let's go with this option. Let's go with OK cancel. That sounds really nice enough. And then the question obviously is, do we get the... And here we have the responses. So we even know which values we will get from the thing. So that we can then make a decision based on that. Okay, we know how to use it. Now let's use it. So this we can copy. We of course need to be able to call the function. So, oops. Void asterisk. Just to make this lowercase, and it doesn't need to be a proper pointer. Good. So where did we put the other thing? Is yeah, let's just put it as the next one. Anti-raise exception, anti-raise exception, anti-raise exception offset +8. Wait, why did we had here this 86? 86 is not right. That would now be 88. And so on. Okay, so we have our message box. And a good approach would be now to add a jump label so that we... So, for example, we know that here call function finish it here is kind of our finish address. So this is the place from which we continue if we want to continue and the application to do something. So let's save this offset. That will, let's make the same type. What was it? It will be a hardcode. So this will be the let's call it the finish label. And we can only use the finish label once we have written all the code that might decide to go to the finish label, because we will set it here. Finish label is equals we need to be finish label offset, finish label offset. And the offsets we generate from data post. That is of course also not the greatest approach. In principle, where does database point? Database points to the gives us the relative position from the start of the thingy. That will be annoying to make this elegant, because we need to ensure that we will always have the right offsets. So for now, we'll just keep this as total offset. And this will then just be code, not code, we had this in the base already. We said this. This. I doesn't like my SC, didn't we define that? Bytes. Oh, it's fine, it's fine. It was just not happy for a second. So this is the offset from the start of our code block, where we need to jump if we want to create some sort of error handling. And the next thing is that we will need to have a jump label to jump to from where we will be calling the function. Which will also be somewhat annoying, because we would want to put the function probably at the very end. Okay, let's do it like this. So we have here at the top our jump to plus 100, and this should be then per data size. Yeah, we are jumping to a arbitrary offset, so we can, in principle, jam as much things in here as we want without disturbing our lower code. So here we will just add the other code, which will be handling the error message. So we should probably document this somewhere for posterity, so we don't forget how the whole thing looked. So somewhere at 0 we start with jump to main code, and somewhere further down we have main code. Then we have here that starts at, so we have 6 plus 0 here. So after this we then just have data section, so data, and we could document it what it all contains, but for now it's not important. Then we have here error handler, and main code will have at some point the finish code, and here is stuff, and the finish code, and then of course we are done. So our error handler, we could make it somewhat simple. We could make it just for now just a breakpoint, so that we just break and then don't do anything but have an broken. And we'll need this as an offset as well. Finish label offset. Error handle label offset. We don't need the label. This is kind of self-explanatory. Right, so here this is just finish without anything, but I'm not sure whether we'll keep the finish. I think we'll get rid of that. Right, so our offset is equals the current position in the code. Doesn't like that because that should be the offset, so that should be like we did here, minus sc. So code is larger minus fc. This is the absolute offset, and there we write our int 3. So for now we have not yet broken anything. I think we can just run it to see that it still behaves as it should. It does not. Something is already broken. A jump offset is not correct. Why? I mean, the thing is, it went to here. Because this, we always incremented this, and now we didn't do that. Why did we use data size? And data size was here, so that we know how far to jump. Well, we have our error handler offset, so we can make data position plus where this thing starts. I'm thinking how to... Because what we want is we would want to make the code such that we'll, no matter how much other things we add there, that will automatically jump to the right position. So if this wouldn't be here, the code would still be fine. So let's put a breakpoint, run it for a second. Okay, so let's remember it so that we don't forget it. That should be 58. And now what we want is just another way to arrive at 58. The problem is that if we take this here, this will not be 58. This will be also it's not really 58. It's just 58 hex. Yeah, it's 50d. Yeah, 5 away, and 5 is the exact size of this this code instruction here. But since this, and we might of course change the size here, since we might want to add a breakpoint. So let's maybe try it like this. We take this minus sc. I don't like that. Wait, this needs to be dereferenced. Right. That's a point. That's a data size. That's just the address of this thing. Okay, so we have the address. So sc. This is the address of this thing. So the value of that. Now we should be able to do this, but it will have different types. this gives us just 1 because it always it doesn't count those 4. So this plus user of this gives us 5, and when we add things here it should keep giving us 5. So right, we said that which one was too big of those two? Yeah, this one was too big, and data position, so we will want to use this minus that, and then it's rebuilding everything, sorry. Okay, it's not quite happy. The data offset. This is yeah, no, it's fine. Right, so so we said we need the data offset what was before to be always 58. That doesn't contain the right value. I put the brackets not where it should be. Or we could minus the thing as well. Yeah, 58 is what it should be. And now if we add some additional code here, the offset should still be 58, and it is. So this part works. We can comment those out since we don't need it yet, and then we just add here our handler so that it's present there. And now it will be a different value, but it should be correct so that the application should not crash. Yeah, it works. We inject where we should, and then everything works fine. Cute. So this takes care of that. Now we can write here as much as we want without disturbing the code further down. I think we can somehow make this upper part more elegant, but for now let's just keep it at whatever is working. Okay, so we have here our handler to which we want to jump, and here we are preparing arguments, we are calling the function, and here we have that we should check for the result. And for now what we'll do is we'll assume it failed even though it did not, and we'll just jump. We have a jump somewhere here, we have a jump, but this is not quite what we want. We want to jump to, because this jumps at this position, so this reads a value from the memory. We don't want that. We just want to jump to plus something. Oh wait, we had such a jump somewhere as well, didn't we? I think we had a conditional jump somewhere. This jump, yeah, this jump. So we already had the needed code. And this is not return address offset, but our handler offset. We capitalized it, so let's keep this capitalized as well. Doesn't make a difference, it just looks better if we keep things consistent. Offset. This is not correct. Word. Right, here. Okay, he was capitalized. So now in principle, when we run it, it should load the DLL, but then bug out to our error handling routine. Assuming the offset is right. So since I am very unsure if we didn't do some mistake, let's add a breakpoint before that code so that we can inspect it. So that we can inspect it before it gets executed, so that we know that we will see if something is particularly wrong. Okay, so we are here in our breakpoint, and then we jump to this offset. Let's see what's at that offset. Oops, 0. Nah, that was not correct. We wanted to jump up. Where did we want to jump? It does not look good. Okay, let's see, why didn't we jump to the right position? First of all, here, before we do our code, I will add a bit of no operations, just as a spacer of sorts. Then we have our code, and this gives us the offset from the start of our code block. The offset from the very start of our code block, and this thing gives us the offset from data PTR, which is there. We need to take those bytes into account. Don't do anything else with data PTR, we just fill it in there. So I think that should be the fix. Oh wait, not that offset. Here. No, not here. Where was that? For code error handler, right for that here. Let's see. So we have here our int3, and then we want to jump to there, 0x. Yep, then we jump where we want to go. And the knobs also do their job. So the thing is, since we have code and data on the same memory region, it tries to interpret the things as opcodes, and sometimes it just produces garbage, sometimes it knows it's invalid, and so on. So if we have enough knobs, then it processes the last thing, then we have a few more knobs, and then we have a nicely processed disassembled instruction set. So this works. So now we can jump here whenever we want, and everything should be fine. So this thing we can, it is not contingent, where is it? Code B, it's just a definition, so it doesn't matter where it lives. So we will move this somewhere, let's say here, because we might want to use this, we will definitely use this thing in other places as well. Okay, then we have here our data offset. And we write data size, that should be fine. And here we can then, we should not call this data because this is like, well, it now contains also code, but for now let's leave it as is. Just main code breaking, and we don't need the end because it just ends at the end. Okay, so this works reasonably okay, and let's say now we will want just to go to the end of the whole thing. Let's see. So we will just make again a jump. But now we need to jump to the right place, and wait, is that the right jump? It's just jump plus something. We should not shouldn't 9. We should keep this cheat sheet consistent. This was okay, but this one, I don't think this will be so easy. So we have our jump code, but we need to jump to the end. At the end, we don't know yet where it is. So either we overwrite the end retroactively, or we could do that, or we make this, we just use our data section, put an address here where to jump to, and then we read that from there. That would also be an option. Just thinking how to make it so that it is somewhat elegant, because no, it will not be elegant in any way, because we will need to calculate the right offset, or because when we have the full address, then we need, well, the address, not just an offset. So this means we will need to have already the memory allocated, which we also don't. So this is in any case really annoying. But this finish offset we won't need. We'll make an word finish, and we'll call it, this is a dot asterisk finish, finish ptr. Let's call it like this. It's not super intuitive, but it's okay. So this is this. And then when we are here, we will need to assign to this thing the right offset. And this is really annoying, because we need the offset to be calculated from where this code is itself right now. Let's just calculate it at the place. So we are here, and what we want to jump to is, in principle, whatever Pepe is pointing to. That is where we want to jump, but we must do the whole thing from the viewpoint of this address. So byte asterisk, so we can do point arithmetics with it. Okay, and so this is where we are right now, or where we kind of think we will be. Okay, Okay, and this thing will be bigger, so we will subtract that. Right. Stern, that was a number. The whole thing will be out when we are done with it. We can try running it and see how far off we are. I guess we probably will be off by, I mean, I'm pretty sure we'll be off by this, so let's just add this as well. And or maybe we will not be, because we are jumping plus direction. We are jumping further down. We are jumping further down, so we need a positive value. So this is smaller. I mean, this should be right. Let's just try it out. Right, so we have here our breakpoint, and we have here our jump instruction. And where did we jump to? We jumped to a completely wrong place. Wait, is it the right jump instruction? Call stack. Did we? We broke something. Let's quickly try it again. Yeah, right. So we are here, and then we have here our jump instruction, which should go sufficiently further down. And we can. If I think it goes the wrong direction, we can disassemble it quickly. Yeah, it jumps up. This is wrong. This is very wrong. But that shouldn't that be a positive number? This is a positive number. That does offset plus 77. That looks correct, so something else must be the problem. And again, and let's inspect. But here, evidently, it wrote a negative number to the thing. Why? D plus plus. Let's put a breakpoint here. Check the memory at the location, so it's 0. That is fine. And the other things are well, other things. Then we go here. We have wrote a lot of things. Our for zeros state zeros, and then when we step here, it wrote 77. That looks correct. It did what we wanted it to do. That is but here it is not correct anymore. CCM. Why? Each point code, right? That is and just for testing, just for testing, write this pattern there and see if this No, it is always overwriting for some reason with not that what we want. So we must have some other bug in our code. We have here our jump, our pointer. This gets incremented so it points further down. We add C9C. Let's check that. So we have here CC jump to summer 90. This part of the code is right. Oh wait. First need to jump to our. That was correct. I was just slightly. We have two breakpoints. We have first breakpoint before we do that. Let's just disable it. That's just confusing me. This one. It was we were looking at this jump and not the other jump. That's why the offsets didn't match that. Now it is where it should be. Okay, so we are here, right? And then we jump to 76, which is, well, it is too far down. We are 4 characters off. Okay, 4 characters off is somewhat what we have expected. We need to jump less far, so minus off. Okay. 72 step, and we are at the undo everything. So let's continue, and our application works as if it wouldn't be hooked, despite the fact that if we inspect it, modules, what is it? Memory modules. It has somewhere our hook DLL loaded, since we just did not execute the other hook. So the resume code path works. What we need now is to check actually whether we need to jump somewhere or not. So this is fine. This line we don't need. Where were we? There. So check for error. So the way most anti-DLL functions work is that on success they return 0. So a load DLL will behave in the same way, and if it was successful, then it should return 0 in the RAX register. So what we just need to do is we need to test whether that register was 0 or not, and if it was not 0, then we know something went wrong, and we need to jump to our error handler. And in the other case, we just continue execution as normal. So we can do that like this. Where's our assembler? Test AX. We don't use the R version but the E version, since the return values are 32-bit and not 64-bit. So that higher half of the RAX register is not used, and if we name it AX, it will only look on the lower 32 bits. Then we have a jump if non 0 to 0x ff bbccdd. Assemble. No, I don't like that. Let's do it line by line. So I check for errors and an error jump. That's one thingy. And the next will be this code. Assemble, copy. We'll reset the space here, so we'll do this time as well. Okay, this we do not need. I will just leave it up there. Okay, and so this is just two. That's super easy. That's just one word. Code per word plus equals 0x. Then we reverse it. C0 85. And the jump replaces this jump. How many bytes are there? These are, okay, this is 1, 2, 3. Jump non-077 BBCC did not take the DD. C6. Let's try. Wait, this one too much. B is fine. That's what we expected, but this gets changed. This will be. This is annoying. This is annoying. That complicates everything. Apparently, the boundary for the data is not at a byte, but they are using some of the bits for something else. Right. So binary 0. Let's go with hex 7. 1, 2, 3, 4, 5, 6, 7. That's the highest signed number. Let's copy this here. Okay, this we don't need. Okay. 1, 2, 3, 4, 5, 6, 7. Okay, so this thing gives us this thing, and this thing is, so if we go from the back, it's from 7. 1, 2, 3, 4. Oh, it's not typing. Hex 7. 1, 2, 3, 4, 5, 6, and then 9. So this is the binary pattern we actually get if we try to use the upper pattern. So let's try something where the last nibble is not set. 1, 2, 3, 4. 1, 2, 3, 4. Hex. Okay, that was for the type for this we didn't need such. Didn't need that calculator. So let's go with 0. And it is also possible that this thing will here automatically add or subtract a 4 somewhere. This thing. gives us this pattern, and this pattern is 7 hex. Yeah, 7 1 2 3 4 5 EA. EA plus 4, no, minus 4, minus 4, so doesn't bring us where we want to be. We could check the documentation, how this opcode is constructed. X. But this does not it says it should be just F085 and the rest should be fine. So maybe it is just adding an offset. Let's try this again. Right, so this gave us this value. Hexadecimal, and if we make plus 4, no, it isn't. Let's just see what the offset is. This is what it gives us. This is what it gives us. Now let's start with this number minus this. I pressed some wrong key, sorry. This minus this in 6. So the length of the whole thing itself is what it's missing. So I guess if we take this decimal plus 6, then we get the right thing. Okay, so it's not that bad, it is just modifying the last two numbers, so this is fine. And so this thingy will be also to instruction 850F 850F, and here we kind of want to jump there, but then that's the question, plus 6 or minus 6. The value was smaller than what we said, so here we need to make this smaller as well, minus 6. Let's re-enable this. But it will not jump, of course, because it does not have an arrow. So let's keep this there, and we need to fabricate an arrow. So move x, 0 x c1 2 3 4 5 6. Wait, is this 6? 1 2 3 4 5 6. And I think 5 is for access denied. So this is 6 characters as well, so it looks kind of like this. No, it's not 6, it's 5. B is here, B8, and here we put the error code 0xc1 2 3 4 5 6 5. Right, so let's comment this. Fake an error. We have our breakpoint, then we fake the error, then we have here our test, which sets the right flag, and then we have here our conditional jump. And then it should continue. Let's see if this will work. So we have here our thingy, then we have our conditional error, error fake, then we have our test, and then we have our conditional jump to... Well, it jumped, but not where we wanted it to. 6, interesting. Would it have worked without the 6? Which would indicate that we have some index problem somewhere, but let's try it. Okay, so zack, 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 and now it jumps where it should jump. Okay, so for whatever reason, well, it works. That's the only thing I care. And of course, if we don't do this, not this, don't do that, can try it, then it will just go over the function, over the opcode, and not go into it. So we have here just a test, just a jump, but as you see, the jump didn't jump. We just continue with the next line of the code. So if we now play, we get to our hook, and then we have our hooks installed, and the thing works as expected. Okay. So we enable our fake error. Backbreak, fake error, can now check errors, and then this can go. And in the simplest case, we can just copy this code to the next check error. I think we can just check first here. Zack. And in theory, we could also have so first of all, we could of course now set a register which will then allow us to know which step failed. But since we are already now running a bit out of time, we only have 45 minutes left. Well, technically we just have half an hour, but we never do the 15 minutes break, so we kind of have 15 minutes extra. So we could try if we have enough time to implement the body of the error handler in a way that will satisfy our requirements, so that it works, and we can really like make then a decision what we do based on which button the user presses when this message box comes. At this point, it's like just labor intensive, because all the needed gadgets to implement this we already kind of know. But let's proceed. Maybe we will be finished in time. So let's quickly reformat this here. I'll just copy this thing. Let's just copy everything to our cheat sheet. Okay, so we need 1, 2, 3, 4, 5. We need 6 arguments. That is mildly annoying, because 6 arguments means we cannot. We need to put some of the arguments on the stack. Be so nice if we would only need 4 of them, but nope. Okay, so I was a bit too optimistic. We don't have everything we need, because I haven't showed you how to make such a function call with stack allocation. We only until now did function calls with functions that have 4 or less arguments, which is a bit simpler. Okay. So this is an argument. It's like this one param thing here. We will need to prepare this as well. Wait, do we? Can we fake around this? We can. Because what it is basically an array of Unicode strings, right? So if we have an array of Unicode strings, or rather an array of... Wait, are these Unicode strings or are these pointers to Unicode strings? I mean, they are definitely pointers to Unicode strings, but it's an array. So what we want to pass here basically is an address, which if you dereference, you will get a pointer on the first Unicode string. So this is in principle identical to the argument which we are putting into here as the DLL name, just that there could be more pointers after it, so we can reuse this already prepared data structure. That will help us. Okay, so we have our break here. Here we have our jump to finish, so here at this point we will be implementing our code. So let's see. We don't really care to save any return value. So we could, for example, now also save like the return code and use it for something. Actually, that's not such a bad idea. We could use the return code and to feed it to this function, so we would know in more detail what went wrong. But then, of course, before we do that, we would need to check if we specify here a different error code, but still the Unicode string, what that would mean effectively for us. So let's go with that was the old one, and the new one will be, I don't know, something like procedure entry point not found or something like that. Procedure not found. Let's see if we make it procedure not found, what the message box will look like. Yeah, in this case it ignores the argument. I mean, we could also kind of abuse this to, instead of passing the DLL, just pass an own string that says something like ignore the strings around. This is the message, this is the error message. Huh. Yeah, one after the other. We can use other registers as well. Let's first try to just get this thing called successfully. So we have a move ECX. Because it's a unique, it's a short string ECX 0x, and here let's get. Actually, we can use this defined, so we don't need to take the numeric value. We can just write like this. That will be the first argument. The second argument, we should copy the thing. This thing. So we know what we are feeding it. Okay, the second argument should be a 1, so move, and what was it? According to the definition, it's a ulong as well. So e dx comma 1. The next one is r8. R8 is also 1. And R9, and move is with just this. And this will be a layer R9, the same as it was here for the layer R8 layer. Yeah, this one. So this actually we can almost. This one is the right one. We'll just use the path here. Undo this. Okay, so layer 9 DL offset path, and then we have we have the two other. We have the response options and the parameter. it should work like this. Move. RSP plus 4 Stern 8, Komma. And then we can put the value, so we decided to use optional cancel. Actually, we can use the, it's defined here, so we cannot use it. 0, 1, 2, comma 2. And the other argument, will be complicated. We can reuse rex. 4, 5. It's the next slot. Rex, and before we do this, we'll do move rex. No, not move layer. Layer rex, comma. And we need a free space somewhere, so error response function address. This is an error response post data plus 8. This is for now 0, then this is then not 88 but 90. 96. But for the level DLL base, will that be correct? It should be correct. Larax, something like this. Okay. Let's start assembling the code. What was it? This was this value. It's 6, so we need those two. 4, 2, B9, and then here 0. Here we can just put the error code directly. I think, yeah, that looks right. Qt move, that is a trivial one. And let's assemble the other one as well. This one is a bit longer because it's one of the higher registers, the non-32-bit one. So this one is 6 and the other one is, I guess, 7. Yeah. So here is just 1. And here is 0, 1, BA. And here we will have a prefix, punkt pb plus plus is equals 0x49. That's the one thing. Then we have 0c, c7, and 1. This one we already had. This one I don't think it will like the I did not like it. 4 times 8 is does not like this. Cool. Well, TR. Okay. Right. So we have here the 4, and then we have here 1, 2, 3, 4, 5. Okay. So this is this many. 49, and then here is just 2, and here is 0x 20, 24, 44, C7. Also, this is not pretty. Let's do it differently. So 0b will keep the 0x for C, and what 0x 0d 8d. That's the same. It adds up to the same, but we have then the 64-bit prefix separate and the opcode in the word. It looks nice. It's the same like I did it here, but I won't now change everything else. That's just too much changing. Is this correct? 20, 24, 44, 70. That looks correct. Okay, next one. Did we have Learax already somewhere? No, we did not. Okay. Learax, comma. I'll put this here as well so that we have that we know what we're doing. So this is actually just very similar to this one. We just need to we have other layers. We should have which layers we have so that we can copy maybe something already typed. Layer RDX, that is close enough, I think. Let's see. So and here we also need to change the order B. No, let's just do it from scratch. Washed. Wait, this line is doubled. So B here is 48 is the prefix. Then we have 0, 5, 8d, and then the value, which is here the response offset. Okay, and then the last thing, and this will need to be corrected because we need to specify that. Zack. Okay, so this has 1, 2, 3, 4, 5 entries. So let's copy this and adapt it. This will be D. Okay, so 48 is the same prefix. Let's test the whole rest changes. 28, 24, 44, 89. Okay, that should have prepared our registers, and just so we know where this comes from. So we have here, what is it here? We made this sub RSP 38 hex, and if we go this hex divided by 8, this gives us 7 slots of space. Actually 4 plus 3, I will say later why. Cool. So the idea is that the stack needs to be aligned properly, and when we make a call, there is a third keyword added with the return address, and then we have like +8, which gives us a nice alignment. And the first 4 you need to always have reserved according to the calling convention, such that the first 4 arguments can be put there. So the idea is that you can have all the arguments of a function in the consecutive memory area, which means that if you are calling any function, you need to pre-allocate space for it such that it can put the 4 arguments there if it wants to, without doing own memory allocation. Because if you would have more than the 4 arguments, then and the function would need to allocate own memory, it would not longer be in one block. And then, however, if you on this would make a call just on the 4 ones, that wouldn't work, because then the alignment for the stack slot for the return address would be well misaligned. So that's why you get the +3 as well. And this is good for us because we just use 2 of them here, +4 and +5, and we could have made +6 to use the last one, that is 3. And if we would want to pass more arguments to the function, then we would need to make the stack basically bigger by another 4 slots and use some of that. So the way memory is used in the 64-bit system is a bit wasteful, but it also kind of gives you a more simplified code, so it's not all bad. Okay, so let's now call a function. We had a call somewhere. Call. Yeah, let's just copy one of the calls. Zack. Right. So this was just a comment. This is now the call. Oops. Just that here we want this one. Oops. Okay, we are still missing evaluating the return values, and we are also missing a well, it's something to crash the application if the user says no or cancel. Yeah, cancel. But let's run it and see how many mistakes. Sure, this doesn't work now because we did not disable the test code. Yeah. Okay, so we end up here in our breakpoint. So let's see CC and then this code here. So we load the registers. Load this register. Wait, something's wrong. No. We are not yet here. We are at a different place. We are faking the thing, and then we. Oh no, we jumped wrong. Something's broken. So we added a lot of code here, and it ended up breaking our. Okay, let's try again. So the breakpoint which we arrive here is the other one. It's this one here, further down. Yeah, here we have our faked error code, and test and then jump, but this thing, apparently to our error handler routine, when we jump there, we jump to the wrong offset, and we are very wrong, because or maybe we just screwed up something, because that actually looks like the right offset. We have our 9s, we have our C, but the rest of the code, it just did not decompile properly. So we are here, we have CC, we have B9 for C, but it is not decompiling this. So I mean, we can make a step. And well, tell me, after we make a step, it decompiled it, but it still shows some question marks. So somewhere in the code here we have some screw up. So let's see step by step. Move ECX, move ECX, and then we have this value here. And this is already not correct because it is a wait, or is it it shows this as too short. Why didn't it work? Let's compile this again. Comma 0 x a c 0 x c 1 2 3 4 5 6, and just make all c's like this. B9. Oh wait, we really have some error here because this is the code and it should only be move ECX B9. The 42 shouldn't be there. Why? Oh yes. That was just a manual mistake. The 42 is already part of the 1 2 3 4 of the error code. Okay. Continue to the next breakpoint. Yes. So move ECX, move EDX. That is also not the right value, is it? 101. Yeah. Because here we also did the same mistake. There should be just be a B. Okay, let's run it again. We jump over the first breakpoint. Actually, we could comment out the first breakpoint. So this is correct, and then the next instruction is broken. I mean, let's assume this will be right. So 1 2 3 4. This is for 9 is fine. 0 C. C0. C0, C7, that's the correct opcode. C0, C7, yes, R move, okay. Then we have this thing, load address, and this is R9 was our DL path offset. So let's inspect the memory at this offset. That looks correct because we have the 80 and 82, so it's like the length and then so the size and then the max size, which is larger by 2. So that looks okay. Then R12 plus what? Okay, now why does R12 does not look right? that is not RSP. RSP is RSP and R12 is R12. Why? Oh, that's why. C420. Yeah, that's a lot of typos. Yeah, that's correct. Cohort RSP plus 20. Well, I assume it's plus 20. Wait, 4 times 8, that's 20 hex. And comma 2, this is correct. And then layer, this address that should just point us to a 0. To a 0x. Yep, okay, that is correct. And then move RSP 28, it's correct. Rex, yes. And then we call whatever is there. 0x. The H and the N should not be there. It looks like an address. Void asterisk. Yes. It might just work, and we might even have some time to spare. Although now we still need to process the result. Now we jumped into it. I want to jump out. No. We got an error message. The function failed. The function failed, and it failed with this error code. Status data type misalignment. Aye. I mean, the most likely candidate for this thing not working is, of course, here. This thing. To be faster, we could try if we can just specify 0 arguments and the error message. No, but then if we specify 0 arguments and it expects arguments, then it's not happy with that. We could go for this message maybe. It still doesn't like it. Wait, maybe we need to specify both to be 0. Nope, this just bugs out. No matter what we do. Well, we can make it produce an invalid error message if we provide all nulls, but that is not the reasonable thing to do. Data misalignment. I mean, for starters, to see if everything else works, let's really try the all zeros hack. Right, so this will be 0. This will be 0, and this will be move R9. Don't we have a move R9 0? No, we don't. Move R9 0. So this is identical to R8, just that this is then C1. No, C7 says this is 1. Okay, so let's copy it. C1. I'll copy that just to be on the safe side and compare it. C1, C749 and 0, okay. Let's try it out. We have not yet disabled the test code. Zack. One breakpoint, second breakpoint. Well, we can provide a message box, and then the rest does what it should. So we are close. We are close to make it work. I think that the problem we are encountering is with this. Am I thinking wrong? Here. This is a pointer, and it contains an address. Faram1 is locally. That should be the same thing. I mean, if we put a breakpoint here. And now I need to enable this code again. If we put a breakpoint here, and then inspect params in memory. Oh, that's not what I expected. Okay, wait, but this will be an address. Let's do it here. Params. The thing is in principle just an address, right? The thing is in principle just an address, and at this address should be a address of a Unicode string. So void asterisk asterisk. That's the address it points to, and the address it contains 2022 and then some buffer. That's correct. We are passing an address to memory, which contains another address. Yeah. This we cannot reuse the variable there. We will need to create we need to make another memory place. Error params. This is still 0 error response. Just that this changes. So here +8 is 100 and what? +8 is 104. 104. Okay, so let's undo this and that and all of this. We use that, okay. But now it will contain null, so it will not be a valid argument still. So I will do a few things. First of all, I will add a breakpoint here, because here we are not yet done with the code, and I will comment out. I will leave the other breakpoints in, why not? I will just add this breakpoint there. So what we now need to do is we need to write at this position the address of our Unicode, of our Unicode string DL name. we could do that. We could do that like now statically, but I think that is also kind of convoluted, so let's try to do it differently. Genau, so here we have our layer. We'll copy this. Oh, because here we get it, we copy this here. And params. So we have this inner Rax. In the Rax register. Actually, we could simplify this. No, we can. We can do it differently. We don't need to do this. We can reuse the R9 register. So we have the address in the register, in the R9 register, but this address still null is well written. So I want to move to the PTR. PTR from R9. Something from where was our DLL path? Yeah, basically something like this, just that we here put the DLL path. Let's see if it will actually like that. No, it doesn't like it. It doesn't like it because it's we can only use a memory access in one of the thingies. Okay, so let's do it differently. The path. What did we get? DL path offset. Here we have code where we then base offset. 9. Okay. Now let's do it with this. So we'll copy this one now. We have here the address. Then we know we can use the Rax register because it's not used yet. So we want to load Rex, the DL path, load address, Rex thing, and so on. So this is the only one that changes. Okay, so only this one changes to 8, and we wanted to make this more elegant. So okay, so now we have this in this, and then we can do that operation. We can move to this from Rax. Nope. Wait, why doesn't like it? That cool. Cool. PTR. Now that makes me to think whether would it work? The typo here, would this work if we would try the other one? I don't think so, but let's try it out just for funsies. Yeah. Yeah. There is no way to make two memory accesses in one. One of them must be a register. 1, 2, 3. Okay, this is a reasonable. Yeah, because we don't have any offsets. That is simple enough. We just take the address at. So let's check if everything's right. So we load to R9 the address from our data block, and then so we have the address of the data block. Then at this position where there are now zeros, we want to write Rex. Yeah, that looks correct. So 4, 9. 0, 1, 8, 9, and the other one was 4, 8, 0, 5, 8, D. Okay, that looks correct. So now we have everything. That should work. Let's try it. I mean, this can, we will leave it for now. Yeah, we will leave it for now. Let's run it. So first breakpoint we ignore, the second breakpoint is this breakpoint, and then we compare. So layer rax move RSP. Sorry, let's start here. Move to then layer rax, then move to R. Wait, something's not right. So we have our layer rax here. Then we have move. Toward R9 move. That is not correct. 1 X. But this one is missing. Why is this missing? Because the call is still there. Somehow it didn't. So this line absolutely didn't take. Wait. 48 FFF, and then we have 48 28. Then we have our. Wait, or am I looking on the wrong line? I'm looking on the wrong line. Here it is. It's fine. So layer rax, move toward rax. Okay, let's run it. No, it's not happy. We still get a alignment error. I'll add a breakpoint here and comment the other breakpoints out so that we don't break where we don't want to break. Apparently I left one breakpoint somewhere. This breakpoint, yeah, okay. This breakpoint should stay here because just a guard breakpoint. This breakpoint we don't need. Okay. Okay, so let's see. So we are here and we have our RCX is the error code, RDX is 1, R8 is 1, and R9 should contain the address of the Unicode string. Which looks correct. But it is still not happy. And our return argument, let's see, move. So layer, wait, what is it? Here's this. Right, so here's our, the option is number 2, and here is the rax and rax, so where we want to write this. Let's see if this address is correct. It should be still in rax. Which is also correct. Not good. We step over this, we just get our error message and it doesn't show the error code. Why? What doesn't it like about that? Well, we are out of time, so I will not fix that now. Well, so that was it for now. I will upload it as is to the Moodle, or maybe I will try to fix it and upload it fixed if I find a quick fix. And well, that's it. As I said during the exercises in the morning, I will start grading on the first week of February, so you have time to finish your not finished homeworks and of course finish the final project. Do you have any questions? Oh, someone wrote that the microphone is not working. The things that Zoom says that the microphone works. I see the thing changing. Well, that someone's microphone is not working. Yeah, that's not a problem. Okay, so I will stop for now the recording and I will look to the questions in the chat.